Okay, hello everyone. I think it's time to start, and I will allow other participants to come in later if they join this meeting. And of course, this meeting will be recorded, and the recording will be post-processed and then uploaded to our official channel after some time. And I think some more people are joining now. So today we have a very brilliant researcher from Hong Kong University to give a talk on the topic of graph language models. And firstly, let me introduce our community. So we are a group of researchers who wants to create a small community to share brilliant thoughts from top minds from top universities and institutions across the world. And I think it's a great opportunity to meet and discuss interesting topics in this series of talk. And I think this is already the 11th talk in this series. And we will upload previous recordings very soon in our official channels. Please stay tuned if you are interested in previous talks. And I think our next step, I will leave the presentation to our speaker today, and he will introduce his work at University of Hong Kong. Okay, now I will leave it to you, and you can start.
Okay, hello everyone. I'm Jiabin Tang from Institute of Data Science at the University of Hong Kong. Today I will give the presentation titled Graph Language Models, that is combining graph learning with large language models. And my presentation will follow this outline. I will first introduce the background and challenges of both graph and LLMs, and then I will provide a brief introduction of combining graph and LLM, namely graph plus LLMs. Next, I will introduce our LLM as predictor methods, namely GraphGPT and HiGPT. And then the final part is Q&A. And firstly, I'd like to introduce myself. I'm a first-year PhD student majoring in data science at the University of Hong Kong, supervised by Dr. Chao Huang. And my research interests mainly lie in large language models and other AIGC techniques, and graph learning and trustworthy machine learning, and other deep learning applications such as spatial temporal data mining and recommendation systems. Okay, so what is the graph data? Graph data consists of nodes and edges, and can be used to present the complex relationships between the entities. You may learn it in the discrete mathematics, and this type of data has extensive applications in many fields, such as social network analysis, drug discovery, and urban computing. Recently, graph neural networks have been proposed to model graph data using deep neural network techniques, resulting in a very significant achievement. However, unlike image pixels that have a uniform RGB representation, and the semantic relationships in different graph data vary greatly, making it impossible to model within a single graph neural network. And meanwhile, large language models like ChatGPT, which are trained on vast data and utilize the increased number of model parameters, have achieved astonishing results in many areas of natural language processing, that is NLP. Particularly, we could note one thing is that their impressive transferability, which enables them to handle tasks they have never been trained on, that is zero shot. So with the strong generalization of LLM, combining graph learning with LLM is a natural idea, and the benefits of graph plus LLMs mainly lie in two aspects. Firstly, LLM can bridge semantic relationships between different graphs using natural language. Also, the success of graph plus can make graph foundation modules and other automatic graph modules possible, which means encode all graphs in one module. So the graph plus LLM techniques can be broadly divided into three main classes. The first one is LLM as augmenter, and the second one is LLM as predictor, and the final one is LLM as agent. LLM as augmenter method utilize LLMs to enhance the original graph data or other downstream data like social recommendation data by leveraging the global knowledge inside the language models. And LLM as predictor models directly use LLM to perform various downstream graph learning tasks such as node classification and link prediction. And LLM as agent approaches, the designed agent retrieves information and plans to solve various graph-related tasks automatically. And in today's talks, I will mainly talk about our LLM as predictive methods, namely GraphGPT and HiGPT. So let's dive into the main content of this talk. Effectively combining LLM with graph learning as a predictor poses non-trivial challenges. The first challenge is how we can feed graph structures into the LLMs in a natural language format or the other format. And that is a question. The second research question is how we can empower LLMs to understand graph structures. That is how to align LLM's ability in reasoning with graph understanding. And finally, how to endow LLMs with the ability to reason step by step for the zero-shot complex graph learning tasks. And generally, we like to figure out, can LLMs be the zero-shot graph learners? That is, if LLM can do the unseen graph tasks. So we like to address these challenges one by one. For the first research question, there are mainly three approaches. First, for specific paper classification in a citation graph, we can just classify the paper with graph structure without graph structure, namely don't provide the neighbors information. But we found that this approach fails even using the ChatGPT, a very powerful LLM in the world. When the paper is in a disciplinary field, which means its neighbors' information may be very complex and also be very valuable. And another method is to feed text-based graph into the LLM. And the text describes the connection information in the prompt. However, it doesn't address the error and it makes a token length too long. We all know that the input content length for LLM is limited. So the last case is the result generated by our GraphGPT, only with 7 billion parameters, but we can effectively input the graph and let LLM learn from the graph. Also, the input token length is controllable in our GraphGPT. So we achieve that by introducing the graph tokens. We regard graph as a sequence of graph tokens, and the overall architecture is shown in this figure. The graph is encoded by a pre-trained graph encoder, and the graph encoder here could be any graph neural networks that such as GAT, GCN, or graph transformer. The graph embeddings are fed into a projector to obtain the graph tokens. And we impose the graph tokens and the natural language tokens concat to let understand the graph and follow the instructions to do downstream tasks such as node classification and link prediction and so on. And in particular, the first part of our GraphGPT is text graph grounding. We utilize graph encoder with nature language alignment. We use the graph text pair and pre-train the graph encoder in a contrastive manner. And the second part of GraphGPT aims to address the research question too. That is, how can we empower LLMs to understand graph structures? Our answer is our graph instruction tuning paradigm. The graph instruction tuning paradigm has two stages. The first stage is self-supervised instruction tuning. We input the unlabeled graph into the LLM and let LLM match the graph tokens with the corresponding nature language content in the prompt. For example, different nodes may represent different papers. We like to let LLM based on the graph tokens and reorder the shuffled paper list. Note that we only tune the parameters of the projector, so our alignment is very lightweight. And the second stage is task-specific instruction tuning. We used instruction data for the downstream task. This figure showed the instruction template of our node classification and link prediction tasks. And then we answered the research question 3 by distilling reasoning ability from a powerful module such as ChatGPT through our chain of thought distillation. So you may ask, what is chain of thought? In our chain of thought is simply add the place sync step by step after your original prompt. And ChatGPT is very powerful, yet closed sourced and cost very may cost them many money. And our GraphGPT with 7 billion parameters is lightweight yet not very smart, especially when we feed some very complex downstream graph tasks. So we use our COT distillation to deal with it. That is, distill the reasoning ability from the powerful ChatGPT to our lightweight 7 billion GraphGPT. And the experimental results show that our GraphGPT outperforms SOTA modules, not only in supervised, but zero-shot settings. And know that we are very first to propose to deal with the zero-shot challenge in the graph learning domain. And there are some results. Also, I like to highlight the generalization ability investigation of our GraphGPT. Specifically, we mix up different kinds of instruction data to obtain multiple data combinations, such as different data sources, different data pattern, that is, whether contain chain of thought patterns, and different tasks, such as node classification and link prediction. And we have some interesting observations. That is, more data will boost module transferability, which means the significant improvement in the zero-shot setting. And more data, but no forgetting, which means the training of our GraphGPT on multiple data sources, it will learn both them and not occur forgetting. Moreover, generalization for multitasking graph learner, which means the multitask instruction data, which means with the multitask instruction data, our GraphGPT tend to be multitasking graph learner, and different tasks can benefit each other. That is, node classification data will benefit link prediction, and the link prediction will benefit node classification. And is our module case study. More detail like projector page, paper, code, and module could be found in this figure. And you are really recommended to scan the QR code to directly access our project page. And there is one more thing. Don't hesitate to give us your star to support our GitHub repo. And we thank all the researchers that is who could give them their star to our GraphGPT repos. Okay, so next I'd like to introduce a very latest work, namely HiGPT, that is Heterogeneous Graph Language Model, which proposes a heterogeneous graph instruction tuning framework for the large language models. So before introducing the technical details of HiGPT, let me introduce some background of heterogeneous graph. Graph I mentioned before or homogeneous graphs, which means there are only one type of nodes and one type of edge. However, in real world, there are a lot of graphs that contain multiple types of nodes and edges. For example, given a graph showing the right figure, there are three types of nodes, that is movie, actor, and director, and four types of edge, that is movie to the director, director to the movie, movie to the actor, and actor to the movie. So we should model different types of nodes and edges independently. We call these graphs as heterogeneous graphs. In contrast of homogeneous graphs, the formulation of the heterogeneous formulation of the heterogeneous graphs contains the types of the nodes and edges, and the feature matrix of heterogeneous graph are divided into different types. Due to the features of the heterogeneous graphs, we have meta relation to model heterogeneous graphs. And an example of the meta relation is is a representation of the relationship between different types of the nodes connected by an edge. And from an edge, E equal U and V. The meta relation is the node type tall U, the edge type rho E, and the node type tall V. And the motivation of our HiGPT is to combine heterogeneous graphs with LLMs to enable LLMs to directly conduct heterogeneous graph learning tasks. But we found some unique challenges. The first challenge is, how can we deal with relation type heterogeneity shift across different heterogeneous graphs? For example, in a citation heterogeneous graph, the node type may be the author, paper, and conference. But in an internet movie database heterogeneous graph, the node type may be movie, director, and actor. The existing heterogeneous graph modules are independently built on different heterogeneous graph, which makes the zero-shot heterogeneous graph learning impossible. So can we build one heterogeneous graph for all heterogeneous graphs? That is a question. So the second challenge is, how can understand complex heterogeneous graph structure? Heterogeneous graphs are more complex than homogeneous graphs, absolutely, because node and edge types and the structures are in the heterogeneous graph. So can we let aware nodes and the edge types and the structures in the heterogeneous graph? That is also a key question. So the third is how to address data scarcity for model fine-tuning for the downstream heterogeneous graph learning. Recent heterogeneous graph model focus on few-shot settings, even one-shot setting, which means during the training, only one sample per class is available for optimization. Not only few-shot, we like to further push forward this research line with zero-shot setting. So all in all, our final motivation is to build one module for any heterogeneous graph with few supervised signals. The overview of our HiGPT is shown in the figure. Our HiGPT encodes any heterogeneous graph into heterogeneous tokens through the pre-trained in-context heterogeneous graph tokenizer, which address the RQ1. And these heterogeneous graph tokens are combined with natural language tokens and fed into the large language models. As for tuning paradigm of our HiGPT, we propose instruction pre-training on a large corpus of heterogeneous graphs and supervised fine-tuning with designed heterogeneous graph instruction to deal with RQ2. So let's step into the technical details of our HiGPT. The first part of our HiGPT is in-context heterogeneous graph tokenizer to address RQ1. Specifically, we conduct graph tokenization with the matter with a heterogeneous graph, and the HG tokenizer is shown in the figure, and it could be implemented using various backbone heterogeneous graph neural network such as HGT, HGN, and HGNN. And in particular, the message passing and aggregation of HGT is shown in this figure. We can observe that the message passing and the aggregating process are node and edge tab specific, which means every node and edge tab in the heterogeneous graphs is learned a set of parameters, such as the theta I, W row, it or the node and edge tab specific parameters. And such features prevent the most heterogeneous graph modules from transferring from one heterogeneous dataset to another one. To deal with that limitations, we propose the adaptive parameterized heterogeneity. In particular, we introduce node tab feature T tau and edge tab feature T row to encode node-aware parameters and edge-aware parameters. For exact embeddings of node tab feature T tau and edge tab feature T row, we present to leverage language as a unified representation to encode heterogeneity. For example, for a specific edge tab relation that is movie to director, we can describe this type of edge as using the sentence like the movie is directed by the director, and the few features directions by the director. And with this sentence, we sorry. With this sentence, we could get the edge tab features using this natural language. And to conduct the initial text graph grounding, we introduce a very lightweight text graph contrast alignment, only alignment the text attributes of every node and the heterogeneous graph representations. Then we propose heterogeneous graph instruction tuning to answer the RQ2 to enable the language models to effectively distinguish between different types of the input heterogeneous graph tokens and the specific nodes within each type. Based on the natural language instructions, we propose instruction pre-training using a large corpus consisting of heterogeneous graph instruction pairs. Specifically, with such pre-training stage, we inject heterogeneous relation awareness and homogeneous relation awareness. And the prompt templates are shown in this figure. And in the heterogeneous relation awareness, we like to instruct to distinguish different types of the sequence of the graph tokens. And in homogeneous relation awareness, we like to instruct to distinguish different nodes in one type of the graph tokens, such as shown in this instruction template. We like to instruct to distinguish the movie type, actor type, and director type from according to the different sequence of the graph tokens, and also to model homogeneous relation awareness, we like to let instruct LLM to distinguish different actor nodes within the actor graph tokens. Then to customize the reasoning ability of LLMs for specific downstream tasks, we introduce heterogeneity-aware fine-tuning to instruct LLM to conduct downstream tasks. And the prompt templates are shown in this figure. Then we further focus on RQ3. In practical scenarios of heterogeneous graph learning, data scarcity often poses a challenge. This is specifically true when using heterogeneous graph to model co-star user and items in the recommendation system, where the sparse user interaction data limits the availability of supervised signals, that is a few-shot setting. In particular, we introduce a novel method for instruction augmentation in the content of heterogeneous graph instruction tuning. This method is utilized prompt engineering techniques, particularly, and we call that mixture of thoughts, MOT, to generate diverse and informative instructions. And the MOT prompt including the chain of thought, tree of thought, panel GPT, and the generated knowledge prompting. With the collection of the MOT prompting, we propose instruction augmentation with the prior knowledge. We prompt the powerful such as GPT 3.5 with MOT prompting to let to simulate the correct answering and the reasoning process. Then we utilize the generated multiple MOT featured instruction to conduct the stage 2 fine-tuning of our HiGPT, which enable our HiGPT to distill the multiple reasoning patterns, that is COT, TOT, panel GPT, from the powerful apps. So then we conduct supervised and zero-shot performance comparison, and the results show that our HiGPT outperformed the short-term baselines. And I also want to highlight the graph in context learning experiments in our HiGPT. We can cut the graph instruction examples with the sequence of the graph tokens, and the observations is that without observation, the performance of our HiGPT are very astonishing. And that is our case study of our HiGPT. And the parts showing the final answer are highlighted in the pink, and the COT prompt is and the COT prompt, TOT prompt, and the panel discussion response are also shown in the screen. More details like project page, paper, code, and module could be found in the figure. And there's also one more thing: don't hesitate to give us your star to support our GitHub repo. And last but not least, if you are interested in urban computing, you are also recommended to check out our Urban GPT. We leverage spatial temporal instruction tuning to boost the generalization of spatial temporal modules to zero-shot downstream tasks. It's also a very amazing work. And that's all. Thanks for listening. Yeah. The next part may be the Q&A.
Yeah, thank you very much for your excellent presentation. And I think this work is very, very interesting. So I think the next part will be the Q&A section. And if anyone have a question, please raise it here. And I think the speaker will try to answer it.
Yes.
Yeah, feel free to type in the chat as well.
Hello, Jiabin.
Hi, hello.
Can you hear? Yes. Yeah, I'm Chuang, and so it's a great presentation. I have to invite you are here to give a talk. And I have a question about in the last slide you show some things about the time series processing, right? I'm very interested because I process some on the time series EMG and EEG or something like this. So do you think it's a big challenge to process the time series with a spatial temporal dependence, those kind of data set? For example, skeleton, it's a time series, yeah, with large language model.
Yes. Yes. Actually, we use the urban spatial temporal data, such as taxi data, back data, accident data, and crime data into the LLM to instruct tuning. And also, we also use the corresponding text data, such as the POI data of different region in the urban with the spatial temporal data into them. And we conduct some very interesting experimental phenomena such as zero shots. And and I think maybe the text data with the spatial temporal data is a key to instruction tuning them, because the corresponding text data are a very nature data format for the LLM. LLM could learn the text data and then learn the spatial temporal data. Yeah, so I think the text data is a key factor in this scenario.
So you said the temporal data, it's mostly about text-based, right? Text-based.
No, yeah. The input of our urban GPT might be two parts. One part is the spatial temporal data, and the two part is
language.
The second part is the language, and the language the language is correspond to the spatial temporal data, such as the POI information of the spatial temporal data and the specific time slot of the spatial temporal data. For example, the text data might be the spatial temporal data is the back, and the taxi data is in the some region of the NYC, and the time range of the spatial temporal data is from blah blah to blah blah. And and I want to let based on the spatial temporal data and the text information to produce his answer according to our instruction, such as predict the next 12 step of the back or taxi data. Yeah.
Okay, thank you. Yeah, very cool.
Yeah, you're welcome.
Yeah.
Is there any questions from the audience? Don't hesitate to unmute yourself and ask questions. Okay, actually, I have a question. So I can see that in your first work, you try to project the graph node embeddings into the latent space of text language model, right? And I'm curious, is it one single token or is it multiple tokens?
Yeah. The token, the length of the number of the tokens are based on the graph, the scale of the graph. For example, if the subgraph you want to input to the LLM is has maybe 10 nodes, and the tokens of our GraphGPT, the graph tokens of our GraphGPT is 10. Yeah, based on the nodes, the number of nodes of the input graph. Yeah.
I see. So I see. So if there are 10 nodes in the subgraph, then you will have 10 tokens in the language model.
Yeah, 10 graph tokens. Yeah, of course.
I see. Thank you. And I do have another question, which is about the data preparation. So I think in one figure you show that you have. Okay, I think this is the one. So you have the on the figure on the right hand side. I think it says that something like the first token represents blah blah blah, and the remaining blah blah blah, and step by step. So I just want to know how you train, how you get the training data, like with the reasoning ability.
Yeah. You may mean the COT distillation, right?
I see. So the
Or
reasoning steps are generated by ChatGPT, and then
yeah.
you take it and
Yeah.
distill it into your language model. Okay, I see.
Yeah, there are some various choices. The first choice is very straightforward. You could you could you can construct the data like the question and the answer is direct answer, such as you instructed the LM and the LM could directly give you answer. That is computer science. But the answer format like direct answer is not enough to fine tune or inject tuning for LM. So we want to let more powerful to generate some reasoning process for the instruction data, such as a ChatGPT could give us the reasoning process in a COT feature, and in our HiGPT we further propose various more than one pattern COT, but other patterns like tree of thought or panel discussion to generate more multiple reasoning patterns to instruct our yeah.
Yeah, thank you for your answering. And I have another more or less, high level question. So I can see that
Yeah.
it seems to work in recommender systems as well. And I just want to know whether this kind of system can be applied to something like collaborative filtering or content-based filtering.
Yeah. I think in recommendation system there are mainly two lines to utilize the power of the LM. The first line is LM as augmenter, and in our group there are two representative work that use LM as augmenter. The first one is rank, and the second one is RLM rank, and they use LM to conduct the user profiling and the item profiling to enrich the information in the item and the users to further utilize the benefit of the LM. And there are also some other research work to utilize the powerful of such as instructor maybe tail rank and other work from maybe Xiaonan group, and they just instruct tuning the LM to let the LM to conduct the recommendation. Yeah, but but some people may think the scalability of the instruction of the LLM to directly perform the recommendation system is a question. But I think if you want to deal with the scalability of the LLM to directly perform the online recommendation, you may use not very large. You could use the small language model, such as 1 billion language model, such as Phi 2 proposed by the Microsoft or other Tiny Llama. You could use the small language model to perform to directly perform the recommendation to deal with the scalability of this kinds of research work, I think. Yeah.
Yeah, thank you. Very nice. And in case that I want to use the language model as predictor, normally in recommender systems, we might have millions of nodes connected with one single person or something like that. In that case, does your method can your method like accommodate like this many of this number of nodes? Because currently, like if you have a subgraph of 10 nodes, then you need 10 tokens, right?
Yeah. Yeah, I think it's a very promising research direction to input a more large graph into the because the commonly used subgraph in our GraphGPT are mainly from hundreds to thousands. But if you want to input the some million or billion nodes into them, I think it's a challenge how to compress the large graph into them. I think is a very promising research direction based of the graph language models. Yes.
Yeah, thank you very much. And is there any other questions from the audience?
I have a question. Can you hear me?
Yes.
Yeah, I can hear you.
Yeah, I have a follow-up question of Professor Zhou. So for his first question, so you introduced instructed fine-tuning, and in I think it's both used in the ChatGPT and also the HiGPT, right? So the instruct or the first phase fine-tuning. So and also you in your response is like the fine-tuning, the size is not very big, only tens of the samples, but you need to make the alignment between the text token and the graph token. But if the size is very small, how can you do this? And also in the HiGPT, you do not only need to align the sequence between the text sequence and also the subgraph sequence, but also their category sequence. If the size is very small, then how can you make sure the LLM understand the latent space, latent representation of the knowledge graph?
Yeah. Firstly, the 10 nodes are only a very trivial example. Actually, the input size of the subgraph into our GraphGPT or HiGPT is maybe hundreds and thousands, and specifically how to ensure that to understand the graph representation. I think your question is that firstly we could use a very multiple prefix task to let them to understanding the graph representation without any labor data, such as the self-supervised instruction tuning or GraphGPT or the or the instruction tuning with a heterogeneous graph corpus. And in our experiments, we found that in HiGPT, if we don't use the instruction tuning with the heterogeneous graph corpus, and we only fine-tune the we only instruction tuning the LLM with the task-specific graph heterogeneous graph data with maybe 3 shots, 5 shots, 10 shots, or 60 shots. The large language model failed to conduct the downstream heterogeneous graph, such as the heterogeneous graph node classification or others. But if we use the instruction tuning with a heterogeneous graph corpus, the heterogeneous graph corpus is a very large heterogeneous graph and instruction pair. If we use that, the LLM could successfully conduct the heterogeneous graph downstream task on even with one-shot downstream task-specific instruction tuning. So we can confirm that within our instruction tuning with a heterogeneous graph corpus without any labeled, we could align the graph our HiGPT or GraphGPT. So our HiGPT or GraphGPT could align the graph structure data with the LLM's reasoning ability. Yeah.
Yeah, thank you. I think I understand your meaning, but it sounds very amazing. So it's only a few shots to make it understand all the such alignment. Thank you.
Yeah, thank you.
Yeah, any other questions?
Hi, can you hear me?
Yeah.
I have a question about the output of HiGPT.
What?
I have a question about the output of HiGPT.
Yeah.
Can you hear me? According to
Yeah,
your
I can hear you.
I find that HiGPT can have a great recommendation results about a movie or a paper about the author, actor, or director. Yeah, but I'm not sure that whether HiGPT can summarize the content of a movie or a paper. Is that the scope of your work, or I think something wrong?
Yeah. The downstream task of our HiGPT is mainly about heterogeneous graph node classification. That is, for example, we want to let out how our HiGPT to classify the movies class, or the author is belong to which specific domain, such as computer science, NLP, or data mining, and yes, but I think describe the node content such as movie content or author or the paper content is also a very promising downstream task, such as a graph QA. Yes, and to some extent, you could refer to this figure. Is our case study. We found that we use various prompt. I want to maybe I want to talk more because you refer to this figure. You could observe that using various prompting engineering techniques, such as prompt to directly answer the categories of this movie, he will absolutely directly give us a response. But if you want to, if you add play think by step, the HiGPT will firstly give the answer and give the reasoning patterns of reasoning process of itself. So the reasoning parts of the HiGPT may contain some content of the nodes or the neighbors, such as the movie's title is blah blah, the movie's actor is blah blah. Based on the movie's director and the actor, the movie should be some specific category. Yeah. And that is my answer.
Yeah, so thank you. Can I think that
thank you.
The HGPT main focus on to output reasonable recommendation results, then get more valuable or more diverse answer.
Maybe the output, maybe the task of the HiGPT is not like the recommendation system, because the recommendation system, you want to rank the item according to a user's preference. But in our HiGPT, the task may focus on input a subgraph which categories of the nodes belong to. Maybe it's a different task, from this different perspective.
Yeah, thank you. That's a really expansive work. Thank you.
Thank you for your question.
Okay, if there are no further questions, then I think today's talk will end here. And really thank you for your very excellent talk and also your very excellent work. And I think people, if anyone is interested in this line of work, please don't hesitate to contact the speaker. And I think on our website you will find all the details of this work. And thank you everyone for joining this talk. And we will finish the recording now, and then the recording will be post-processed and uploaded to our official channel very soon.
Thank you very much for the organization.
Thank you everyone. Thank you.
Thank you.
See you.